Hello friends, welcome to yet another interesting video. In this video we'll talk about active high pass filter. We'll talk about first order high pass filter. In the previous tutorial we talked about active low pass filter, and during that discussion we figured out that it is very important to understand the functioning of the non-inverting amplifier circuit in the filter to understand the entire functioning. So once we determine the functioning of this particular area, all right, so which gives us a few important conclusions, like V naught is equivalent to twice of V1, considering R1 and R2 are equal, and this ideal characteristics VD is 0, In is 0. So you could see that derivation from the previous tutorial, but in this tutorial we'll straight away take those inferences and use them. So talking about the active high pass filter of first order, we know that only this section will give me V naught to be equivalent to twice of VA, right? So this is what we infer from our previous discussions. Now in this particular case, like we discussed in the previous tutorial, we need to find VA in terms of the voltage drops across the passive components R and C in this case. Now if you look at the basic fundamental difference here, this C features here in the series arm to the input voltage, whereas in the low pass filter the series arm used to have R, so it is reversed. But that wouldn't make calculation any tougher, because we simply want to find VA from the perspective of the non-inverting terminal and the inverting terminal difference. So VA is going to be R upon R plus 1 upon S into C, and of course multiplied by V1. So this is simple Kirchhoff's voltage rule, and then VA becomes equivalent to this equation. I'll put it as star, so you can note down this equation carefully. And from equation number 1 we know that VA is V naught upon 2. So my V naught upon 2, substituting VA as V naught upon 2, I get a very important relation of V naught upon V1, which is what we are trying to find, because this is nothing but the transfer function, and transfer function is what is going to determine if the signal is being attenuated or not. So if you look at the transfer function of this circuit, you see that S features in the numerator, and it is of the order 1. It has a power 1, so it is a first order filter, of course, but at the same time it features in the numerator. That gives me a few inferences, and those inferences are summarized as because S is j omega, so gain becomes high and constant at higher values of omega. So when omega goes high, the gain also becomes high. The gain is low at lower values of omega. So if you look at this direct relationship of gain with the frequency, it exactly replicates a high pass filter circuit characteristic. So this circuit represents a high pass filter section. So that being the fundamental difference, And as I mentioned in the previous tutorial also, when the operational amplifiers are connected in different ways, we get different types of filters, whether they are low pass or high pass or first order or second order. So this is one such example of a filter which is more complicated than our filter. So it's a second order filter. The first order filter is a simple one with two passive components connected to the input voltage. And if we talk about the cutoff frequency of this high pass filter, it again is represented by Fc, which is 1 upon Rc. So you need to commit this to memory for numerical purposes, otherwise this derivation would suffice, and this derivation clearly states that this circuit replicates the high pass filter's characteristics in first order. And I hope this quick tutorial was of help. If you liked the video, give it a thumbs up, consider subscribing to the channel. I'll see you around. Take care. Bye bye.